Hi there, welcome back to our video lecture in ENSC107, and this video will be moving on to our next topic, which is the accelerating vessels. This topic is also referred to as relative equilibrium. So the main the main concept here is that when we have example, when we have a static fluid and we have this fluid contained in a container, we have already learned that the pressure only varies along the y direction. Okay, so our pressure equation from the hydrostatic equations, we have delta P is just simply equal to the negative of the unit weight times the delta H or delta Y. Okay, so we have learned this, and we know that this is the hydrostatic equation. Okay, so now what will happen if we have the same fluid, static fluid? Static fluid in the sense that it is in equilibrium with respect to this container, but the container is in acceleration. Okay, so because of the acceleration motion, or because of the motion of this container, then we will have a something like a we will have a difference in the free surface. Okay, so difference in terms of the geometry of the free surface. So initially we have a straight line. Let's say this is our initial position of the free surface, but then if it starts to accelerate, and let's say we have a constant acceleration, then this straight line actually becomes tilted or slanted. Okay, so this slanting position, so imagine this container is accelerating. It is accelerating continuously at a constant rate, and therefore this will be this slanted position, or this slanted line, is the new surface, new free surface position. Okay, so it will maintain its tilted position according to the accelerated values, or the magnitude of the acceleration. Okay, so because of the tilting of this free surface line, then we will have a difference in the hydrostatic equations. We will deviate somehow from these hydrostatic equations, but still we will use the concept of the fluid statics in deriving the equations. Okay, so again, we will have an accelerating containers, and we can say that the acceleration can be acceleration or translation. Okay, so translation, when I say translation, that can be translation or acceleration along the x, right, or along the y-axis. Okay, and the other one is, it could be, we can have acceleration that's rotational in nature. Okay, so rotational nature, and then this one is translational, or we can just refer to it as linear. Okay, so this one is linear, and our linear acceleration can be along the x or along the y. Then another one is, we can have an acceleration if it is undergoing a rotational motion. Okay, so for now we'll develop, or we will derive an equation for a container that's undergoing horizontal acceleration, or acceleration along the x. So now let's draw first our situation. So we have our container right here, and it is filled with, let's say, with a fluid or a liquid. Okay, so that's the initial position. But once it gets accelerated, then it will have a tilted position. Okay, so this is now our new surface, or our new free surface. Okay, so let's say we have this universal coordinate systems. This is our x direction, and this will be our y direction. We have a constant acceleration along the x direction, positive x direction. Okay, so if we try to consider a differential volume or an infinitesimal element, okay, so let's consider this and let's zoom this out. Now if we zoom this, what we'll have is, okay, so let's translate this. Let's translate this universal coordinate system, or the UCS. This is our x direction, and then this will be our y direction. Okay, so let's try to expose the forces. We'll do a free, we'll do a free body diagram of this infinitesimal element. Okay, so along the y, what we will have is the force from the pressure. Okay, and we'll also have the weight of the infinitesimal volume itself, right? So it's actually the same as the hydrostatic equations. Okay, so these are p sub y, right? P sub y. Okay, since we are dealing with force, then that should be p sub y times the area. Okay, so that's the area underneath, area perpendicular to the direction of the force. Okay, so this is our p sub y. This one will be p sub y plus, okay, so for now, let's, instead of using the notation dy, dx, and dz, we'll use the delta. Okay, delta x. Okay, delta x. This one is delta y. Okay, so it will just be the same with the dy dx if we take the limits. Okay, so for now, let's just use the delta x and delta y. Okay, so we have here py times the area, and the area is just simply delta x times delta z. Let's try to draw in 3 dimensions. Okay, so this is our origin, then the x direction is here, and then this will be the y direction, and then this will be the z direction. Okay, so therefore the area will be, okay, so this is delta x, this is delta x, this distance, and this one is, okay, this direction or this length is delta z, because that's along the z axis. So therefore the area is just simply delta x times delta z. Okay, so the next one is this force on the top surface. So that's py plus, okay, so since this is delta y, then this is py plus delta y, of course, times, we need to multiply that to the area. And this one is the weight. So the weight is just simply mass times, right? The mass times the gravitational acceleration. Okay, and right, so that's the mass times the gravitational acceleration. Okay, so if we do, so uh, let's try to sum the forces up along the y direction. Okay, so summation of forces y, and let's say this is positive, and along the y direction there's no acceleration, so therefore summation of forces y is equal to 0. And we have derived this in our previous equations. It's exactly the same. Okay, this let's say this type of situation is exactly the same from the from which we derive our hydrostatic equations. So let's just write this is exactly the same. Delta p negative the unit weight times the delta y. Okay, so it's exactly the same. But for the x direction, summation of forces x, that's not equal to 0 because it's actually accelerating. The container is actually accelerating, and so the summation of forces along the x-axis would be m times the acceleration along the x. Okay, so now let's write the forces. So we have forces right here. Okay, so pressure force again, and we'll have a pressure force on this side as well. Okay, so let's say this is px. So since we're dealing with forces, we need to multiply that to the area, and the area right now will be since this is delta z and then this is delta y, then the area along the x-axis would be the area, if we're considering the motion along the x-axis, would be simply delta y times delta z. Okay, so we have here. Okay, so now let's write down the forces. So p sub x times the area minus, okay, so this is positive because it's going to the right, and then minus the p sub x plus delta x. Okay, p sub x plus delta x times the area. It's equal to m times the acceleration along the x-axis. Okay, so what is pressure at x? Okay, so the pressure at x can actually, if this is our tilted line, we can see that this pressure at x, right? So this height from the free surface to this point is what we call as let's say hx, and the distance from the free surface to here, this is hx plus delta x. Okay, so the difference from the between the points would be delta h. Okay, so now let's write the pressure is simply the same as the hydrostatic equations. It's just the unit weight times the height. So the unit weight of the fluid times the height, let's say this is hx times the area. And what is the area? That's just delta y times delta z, okay, minus the h, okay, at this point, along this point or along this line, that's just the unit weight times hx plus delta x, right, times delta y times delta z, okay, is equal to, right, so let's continue right here. It's equal to the mass, but the mass, okay, recall that mass is just simply the density times the volume. Okay, and our volume This one is just delta x times delta y times delta z. Okay, so that's the volume of the cube, which is delta x times delta y times delta z. Okay, so if we substitute the values right here, what we get is rho times the volume delta x times delta y times delta z times the acceleration along the x-axis. Okay, so we can since we have delta y times delta z on all terms, or in all terms, then we can just simply cancel this out, right? Okay, and we notice that in the right hand side we have the same unit weight, and therefore we can factor it out. So hx minus hx plus delta x times the unit weight. Okay, and that's equal to rho times delta x times the acceleration along the x. Okay, so in terms of the geometry, this is delta h, and the delta x is actually this portion. This is just delta x. So as you can see here, this is delta x, the distance, and this is delta h. Okay, and from this geometry we can actually obtain the angle. Okay, so let's combine the geometric terms. Hx minus hx, or we'll just write delta h over delta x is equal to rho times a sub x, or over the unit weight. Okay, but this unit weight is just simply rho times the gravitational acceleration. Okay, so rho divided by rho, and what we get is a sub x, or over g, delta h over delta x, which is just equal to this delta h over delta x from the trigonometric relations. This is just equal to tangent theta is equal to ax all over. Okay, so what can we get from this equation is that from this equation, actually also this one, you can see that if we know the acceleration, then we would be able to determine, right, the angle. Okay, so or the inclination angle. Okay, also we if we know the acceleration, we can also determine how high, right? So how high it will rise right here, because once we know this height, okay, once we know this height, then we can actually determine the overall height, okay, from this point to the point of concern, let's say this one. So at least at this point we would know the pressure, and if we know the pressure, then we can determine the force. And if we determine the force, then we can actually design the container, the thickness of the container. Okay, so the importance is that if you don't consider the acceleration, okay, so let's just say you only consider the static condition, but the actual situation is that the container accelerates. So if you don't consider the acceleration, then the pressure that you would compute, or the pressure that you would obtain, is only up to this level. So it is lower as compared to the ones that you compared to the ones if you consider the acceleration. Okay, so again, if you don't consider the acceleration, the pressure is only let's say this one, p let's say pa. Okay, but if you consider the acceleration, you would see, or you would have a larger value of the pressure. So this is PB. We can see that PB would be greater than PA. Okay, so greater pressure means greater force. So at least you would be able to design the container or the materials appropriately. Okay, so if we write a summary, if let's say we have this linear, and then we have let's say rotational, and along the linear we have acceleration a along x, and we can have acceleration along y. Okay, so the equations, if we have an acceleration along x, is that along the y, so along the y and along the x. Okay, so along the y we have still the same hydrostatic equations, but along the x we have an additional equation, which is tangent theta is equal to a all over g. Okay. Note that this equation only applies to let's say purely along the x-axis. But if your situation is an inclined, let's say it is accelerating along the inclined surface, then you would have to use a different relationships, which is just tangent theta is equal to ax over g plus minus a sub y. Okay, so you have a portion of the acceleration along the y right here. Okay, so this is for the inclined, and it is purely x. Okay, so now let's try to solve one problem regarding this acceleration along the horizontal axis. Okay, so for the problem 4.1, this is actually taken from the textbook by Gilisania, Fluid Mechanics and Hydraulics, revised edition. Okay, so a closed horizontal cylindrical tank, 1.5 meter in diameter and 4 meters long. Okay, so this is the diameter of the tank, and this is the length. It says that it is completely filled with gasoline with an SG of 0.82 and accelerated horizontally at 3 meters per second squared. Find the total force acting on the front wall and the rear wall. Okay, so we are asked to find the forces on this rear wall and then this front wall. Okay, so again, we have already discussed that because of the acceleration, then the pressure variation, it's not just equal to the hydrostatic equation. Okay, so it would be larger, or that would be different depending upon the direction of the acceleration. Okay, so for the solution, since we have the acceleration along the x direction, then our working equation would be to find the tilt angle, or the tilt angle, or inclined angle. Okay, so that's tangent theta. It's just equal to our acceleration that's along the x all over g. Okay, so since we have this a sub x, therefore we can solve for theta. So theta is just simply the inverse tangent of ax all over g. Okay, so our AX is just 3 meters divided by 9.81 meters per second squared, and we get 17 degrees. Okay, so if we try to sketch the given, this is our let's say this is our tank. Okay, and then let's say this is our center line, and it says it is completely filled. Right, from the problem it says it is completely filled. So in other words, the level of the fluid is up to this point. Okay, so initially this would be the rest position, or initial position. Okay, so because of the acceleration, then we will have a tilted position. Okay, so this is actually arbitrary because this is enclosed, but of course the effect of this movement of the fluid, then it will have a pressure that is equivalent to this height. Okay, so let's label this. This is our theta, then this will be our okay, so from this point to this one, this will be our delta H, and this one is our delta X. Okay, so we have delta X as 4 meters, and this one that's delta H, that's the unknown. We have already solved for the tilt angle, so therefore we can solve for this, because once we solve for this delta H, then we can consider this let's say this height from this point to this one, then we can solve for the pressure. Once we solve for the pressure, then we can solve for the forces. Okay, so this is our rear wall, so let's say this is R, and then this is our front wall, and let's label it as F. Okay, so number 3, okay, solve for delta H. Okay, so since we have the angle, then delta H is just equal to tangent theta times the delta X. So tangent theta is tangent 17 degrees, okay, times delta X, which is 4 meters. We get 1.22 meters. Okay, so in other words, if we sketch it again, make a sketch again, it would be something like this. This is our rear wall, this is our front wall. So if we have this line, then this height, this is equal to 1.22 meters. And by the way, I think I'm running out of time. We will continue this discussion in the next video.